Hi, I'm Charles Preston, and this is the second audio communications lab, part of the Emanations Lab series. It has to do with communicating data between computers using an audio channel, how that channel can be interfered with, signal-to-noise ratio, and how we can overcome some problems with more complex modulation schemes instead of just trying to overpower the noise to create a better signal-to-noise ratio. Let me first introduce the physical lab aspects. There are two Linux laptops and two Windows laptops involved. The Linux laptops are each running software called FLDIGI. This one is going to be transmitting, which it's doing right now, and producing a signal over here on the screen of the spectrum analyzer on a Windows machine. If I turn that off, clear the screen, clear this screen, anything that we send, we can easily tell from whatever went on before. In addition, there's a signal generator here. The signal generator can, from one Windows machine to the monitoring Windows machine, each of these computers is separated by several feet, generates a solid or steady tone. The spectrum waterfall shows that the frequency is unvarying as we go through time, and the brightness of the color shows the loudness or intensity of the tone when it reaches the microphone at the monitoring spectrum analyzer Windows computer. This is a tone very much like a whistle on a steady frequency. We can also generate a different type of tone by making it vary in frequency. This would be something like, and that's going to make it hard on our communications channel over here. That's also operating on 1000 hertz, frequency 1000 hertz. I'm going to first turn the interference off, make sure we can communicate. Incidentally, both of the Linux laptops have live microphones and live speakers, and because they're anticipating getting coded transmissions, coded modulated signals, they try to decode them, and occasionally they come up with garbage when there's no signal, like that as an example. If I type into the green window, as it's sent, it will appear in the yellow window. When it's received on the second Linux computer down here, it will be printed out. If I turn the transmitter on, you can see that it sends whatever's in that window. At a high signal-to-noise ratio, like what we're seeing in the waterfall display here, the background, that is the noise, is very low, represented by a dark or dim blue color, whereas the tones that are being transmitted and being turned rapidly on and off in a complex pattern to send the characters are quite bright. High contrast, they stand out. This is a high signal-to-noise ratio. This particular mode of transmission does not have any kind of error correction. Once I turn on some interference, which would be this sweeping back and forth signal, right on, centered on the same frequency as the communications channel, and try to send some more information. You'll notice that the bottom Linux machine, the receiving machine, is picking up noise. Now you'll notice that because there's no error correction and no requests for retransmit, that is, the transmitter sends it, the receiver either picks it up or doesn't, it's decoding what it thinks it sees as characters, but due to the low signal-to-noise ratio created by the interference, we can't successfully transmit information. What we could try doing is using the processing power available in computers, digital signal processing, in order to overcome that type of interference with modulation complexity. So I'm switching to another scheme that uses more complex modulation to see if we can overcome that kind of interference. I'm going to clear this channel, or this window, and start typing into this. And now when I turn the transmitter on, it will try to transmit, it will encode that information. As it encodes it and sends it, makes noises in the computer, out the computer speaker. They will appear up here. If the receiver can receive the information, it will show up on the second Linux laptop with an air gap between the computers down here. This particular mode does have more complex processing. That's why it takes longer to encode here and longer to decode here. However, it also has error correction. So if it can overcome the signal to noise ratio, if it has a better signal to noise ratio, or if it can successfully operate at a lower signal to noise ratio than the previous mode, then we can successfully communicate again. And that's what we're doing now. As far as loudness, you notice that the sweeping signal is pretty intense, pretty bright, compared to the average intensity of the Olivia communication signal. Nevertheless, the error correction is able to get the message through at the price of modulation complexity. I'm going to throw in a little more noise by turning on a noise generator that creates wide spectrum noise. And you'll notice that the wide spectrum noise is approximately the same loudness and covering most all of the frequencies that are being used as our audio communications channel. If I go back over here, it will encode it in the yellow window and transmit it over the audio channel. And if it's successful, it will show up on the second Linux computer. So despite the broad spectrum of noise here, you can send information successfully. If you have any idea what type of noise environment, signal to noise environment, you can try to design around it. If I increase the noise level, you'll notice the noise, broad spectrum noise, getting more intense, brighter in color, tending to swamp out the Olivia mode signal. But we're sending it. And with some processing power being applied, it's able to pick the signals out of the noise and decode and error correct them. In fact, I can turn this up to a maximum. It's getting really loud now. That's the loudest it will go with this particular noise generator. As you can see, despite the fact that the communicating signal has almost completely disappeared in the noise, this particular protocol, with the use of a lot of processing power, is able to operate at very low signal-to-noise ratios and still get the message out. This is an indication that if you can apply enough processing power, and if you have information about the type of noise environment, you may be able to design around it, continue to communicate, even with severe noise. That's the end of the demo. Thank you.